Hello, my name is Grace Papadopoulos, and I am the team lead for CySat. It doesn't like the spacebar. We are an ongoing M2I project. We currently have 14 members, ranging all the way from freshmen to seniors. And we come from a couple different majors. So we have a lot of aerospace engineers, but we also have electrical engineers, a computer engineer, and a business finance major. The primary goal of CySat is to establish a platform for future ISU satellites and provide a real-world application for our students to test their knowledge and the things that they learn in class. So basically, our primary objective is to hold these people here and making sure that they are learning through using the CubeSat program. Our secondary objective is our scientific objective. It is to demonstrate the CySat platform and adapt it for use with the University of North Dakota payload. This year actually, our main focus will be on the collaboration with the University of North Dakota. They are working on an optical payload that is a technology demonstrator for a future near-Earth object mission, so it would go eventually around an asteroid. However, this will be orbiting the Earth because it's just a technology demonstrator. The team is broken down into 5 different subsystems. We have the mission analysis team, power team, command and data handling, structures, and communications team. And after this, I'm going to hand it off to each of our subsystem leads so that they can explain everything in depth. Our first team is going to be power.
Hi, I'm Carolyn Riedel. I am the team lead for power. My team members will introduce themselves. Sure.
I'm Derek Johnson.
And I'm Miriam Wilson.
We're also going to do a quick overview of the system. It's composed of 2 parts. There's the power board and then the solar array. The power board is provided by Clyde Space. It has a 20 watt-hour battery and an integrated battery heater, so we never have to worry about that getting too cold. And the cool thing about it is that it has individual current and voltage readings for each of the side panels, so we can tell exactly how much power each side is getting. Next up is our solar array, and it's a hybrid design using Spectralab CICs, which are the larger cells, and those are fully encapsulated. And we're going to put those on 4 sides, and then we're going to use Spectralab's task cells, which are smaller, and they allow us to customize the arrangements on sides. This is an old setup for the solar array. When we get the geometry from North Dakota, we'll be able to redo it to fit their cameras. Right now, they're thinking about doing two cameras at possibly 90 degree offset. So we'll be able to modify that using the task cells. Now the task cells do not come encapsulated, so we'll need to go and encapsulate them ourselves. We're just going to attach them to the side panels with solder paste. And the CICs, because they're a little bit heavier than the task cells, we need to use a double-sided adhesive as well as the solder connections. Our goals for this coming semester is to redesign the side panels to accommodate for UND's cameras, and to revise the power budget to make sure that we can support the new mission. We're going to continue testing our old solar array designs. So we can perfect the connections and the design and try to optimize the construction process. Next up is structures.
Hello, my name is Raymond Sukat. I am the team lead for the structures sub-team, and I'll introduce my team members right now.
Hello, I'm Travis King.
Hi, I'm Deshaun Kanaganagan.
Hi, I'm Ryan Massey.
All right. And this is going to be a quick overview of what structures, what our current state is right now, and then our future goals going on with the rest of the semester and eventually the rest of the year. So our current state right now is we have a structure complete for the Softronics mission. That is coming over from last semester, but what we're going to be using it for is as a baseline to go for integration into the UND mission as well. We also have an estimated mass budget as well for the UND mission coming off of the materials that we were using for Softronics mission, and we do have working SolidWorks models of it. And just to go into our mass budget right now, we have a mass budget last year from the Softronics mission, but we're using that to estimate our UND mission, with really the only major change right now being the camera payload. And our weight limit, I believe, is 1.33 kilograms. So as you can see, we are well under that limit, and there is room to work with. And our future goals right now is we're going to continue working on relevant calculations like finding the center of mass for the satellite, moment of inertia as well, gain the full integration of the imaging payload into the CubeSat. And then we also want to do some actual structure testing right now in thermal environment, vacuum environment. We also want to do vibration testing. And then eventually we want to work with the mission analysis team and move the SolidWorks model into SDK so that we can get a better idea as to what kind of orbit we are going to be working with and what our flying parameters are going to be. So with that, I will hand it over to mission analysis.
I'm Peter Papadopoulos, the Mission Analysis Team Lead.
And hello, I'm Ryan Peterson.
So currently, Mission Analysis has been performing analysis using SDK to determine potential access times and lifetimes for the potential orbits we have. And we're also working with SDK and learning how to do more detailed and advanced analyses. And we've been developing a mission timeline for the University of North Dakota's mission and working on the NASA CSLI proposal for our Softronics satellite. So our satellite with the University of North Dakota is going to be launched from the International Space Station. So we use that orbit for our simulations. And we made a few assumptions that are based off of documents written by AGI employees, the company that creates SDK, about CubeSat orbit simulation. So we use 3 different atmospheric models, which are all very commonly used. And each one gave us a lifetime of around 10 years, which is well within our maximum lifetime of 25 years and more than enough for our goal, which would be about 3 months for our mission. And we calculated the access times for this orbit. And you can see there the minimum and maximum ones. And our mean duration would be around 577 seconds. And here is a 2D graphic of the satellite within range of Ames. And here's the graphic in 3D. And our goals for the future are to finish developing our timeline for the University of North Dakota mission and create an accurate model of CySat for use in SDK. So the 2 ways we're going to look at doing this is either importing our model from SolidWorks or creating a new model altogether using SDK's modeling software. And then we're also going to try and perform more advanced analyses and calculate other things such as the exposure time for the solar panels. And next will be communications.
My name is Ian McInerney. I'm the team lead for communications.
Hi, I'm Jacob Goldenberg.
Currently on communications, we're tasked with building a ground station software. We currently have orbit prediction using 2-line element array data that we can get from NORAD or the Air Force. This is then coupled to automatic antenna pointing and satellite tracking systems. We currently have basic communication with the OS board using either a local serial port, or we can also remotely use the ground station software on a remote computer with a serial port plugged into the computer. In the future, we will be taking into account automatic Doppler shift compensation to create a full autonomous tracking system, so it will control the radio and rotator to make it so we do not have to have manual control over that and can get the fine-grained adjustments we need to maintain contact during the entire orbit period. Telemetry decoding, display, and logging is also one feature we will be adding. This will allow us to more easily look at the data and observe the satellite to make sure all the power systems are operational, the data storage is operational, and we have no major problems that we have to address at all. We will also be having commands for we'll also be having places to send commands to the satellite. That will be in the GUI as well. So that way we can tell it to either, if we have to, power down the radios, change the radio power, change how often it's gathering data, or tell it to downlink data, or stop logging housekeeping, begin logging more housekeeping data. So if we have to do more analysis, we can change what we're reading. This is a current screenshot of the ground station. You can see here we have a main screen for showing the orbit as it's passing over Ames. We also have multiple other orbits that could possibly be in sight of Ames, so we can judge which one's a better one to track on in this case. We have this so we can actually track any satellite right now. So that's how we're testing this, is by trying to track other satellites. On the actual satellite, we're going to be having two sets of antennas. One is a quarter wavelength V dipole for transmission on the 440 megahertz amateur band, and the other one is a half wavelength monopole for reception on the 2 meter amateur band. Here we have some plots showing the V dipole and its radiation pattern. We have a nice spherical radiation pattern around the satellite, and so what this gives us is a nice uniform gain around the axis, so that if we're tumbling, no matter how we're tumbling around there, we can always make sure we get as much power as possible. Using this simulation, we were able to determine that we have an effective radiated power of about 3.5 watts. That is with the radio actually running at maximum efficiency, which is unfortunately only 25%. But at that point, it's outputting 2.28 watts apparently, and we have approximately a 2 dB gain on the antenna, which gives us that final value of 3.5 watts approximately. Goals this semester are mainly going to be getting the whole communications link up and running. To do that, we have 3 major steps that we're going to be going through. First one is to get our ground station radio, a Kenwood TS2000, communicating with another off-the-shelf amateur radio handheld, a Kenwood D72A. That one we actually did have working this past week, so that goal has been accomplished. We will then be trying to get the actual payload radio, the Helium HE100 radio, communicating with that off-the-shelf handheld. That way we can have both radios in the same room, so we know that we're not going to have any sort of link issues in terms of concrete in the way from our basement to the ground station or anything like that. We'll then be trying to get the actual Helium radio talking with the upstairs radio, the Kenwood TS2000, as the final step, so we can close the loop and make sure the satellite can talk to the actual ground station equipment. Next, Jake with Command and Data Handling.
Hello, my name is Jake Dreyhaus. I'm the team lead for the Command and Data Handling team.
I'm Chris Lawson.
So the Command and Data Handling is responsible for all the software that's going to be running on the satellite itself. It does bleed over a bit into the communication side of things with protocol design, making sure that protocol can easily be handled by the satellite. And a lot of the CySat as a platform comes through in Command and Data Handling because it's not exactly modular, but there are a lot of components that go in just the operation of the satellite. It's divided into basically 4 layers. At the bottom is the actual hardware, the hardware features of the microcontroller, as well as other components of the satellite. That gets abstracted a little bit by drivers, and then at the 3rd layer up, there's the sort of service tasks that run and present these features in a usable fashion to the highest level tasks, which are things like communications, and then of course the data logging, overall payload mission type tasks that run and do all the top level logic handling, input and output, monitoring the satellite and communicating that back to the base station, as well as being able to adjust the orbital parameters, or not orbital parameters, but functional parameters of the satellite while it's in operation. And as I mentioned, the protocol is, it's a fairly simple ASCII-based protocol. It begins and ends with 2 characters, a start character and a stop character. There's an example of what the protocol sort of looks like there. The commands have certain types and subtypes, and then there is a checksum at the end, which is just simple parity. Currently, in the future, we'd like to improve it so that it would contain a cryptographic signature so it can authenticate messages that would have some sort of impact on the satellite to prevent just sort of rogue commands from going to the satellite. Some more detail on the communications protocol. It'll have to be able to monitor the satellite performance and the configuration. This is handled with query and result messages, so we can query the satellite and it can respond with the battery levels or the time it's been in orbit or the amount of data it is stored. We can send it commands to adjust these parameters, so we can command it to cease transmission. We can command it to adjust the data gathering frequency. And then, of course, we have to also be able to establish a downlink so that it can just send and download a bunch of the stored data so we can then analyze that on the ground. The goals for this semester is to begin testing the drivers. All the low-level and mid-level drivers are written. Some of the more abstract tasks have not been completed, but testing the low-level drivers will have to come first. The data heap that will be used by the satellite to store the large quantities of data that will then be downlinked at a later date, that needs to be implemented. It has been designed. The init system has been implemented. It's not in a particularly tested state, but it does bring the satellite up and is tolerant of unexpected reboots, both during initialization and later. And then the protocol needs to be finalized and fully implemented. Right now it's bare bones implementation and a somewhat flushed out definition of the protocol as a whole.
Again, I'm Ryan Peterson, and in addition to working with mission analysis, I also help manage this year's project budget. And what's unique about this year is that our budget is significantly cheaper than our previous project due to the fact that the University of North Dakota is purchasing all the main components for the satellite. So our budget came out to $2,176. This is allocated out between the cost of supplies for a breakout board, the registration costs for the SmallSat conference at Utah State University, and then the traveling costs associated with going to the conference. Another option we had was registering only 4 team members as opposed to 6, which would mean we could also rent a smaller vehicle with a lower mileage rate. And if we decided to do this, we'd be spending $1,576. And Grace.
Hello again, I'm Grace, for those of you who don't remember. I'm going to talk about our project plan for this semester and the next. Working with UND, University of North Dakota, we have been given a delivery date for January of 2016 for our NASA launch. So pretty much for the next 2 semesters and the summer after that, we're working on getting the satellite to completion. So our goals for this semester specifically are complete software integration of the satellite, as well as you heard from communications, completing a full radio link between the ground station radio and the onboard radio, as well as revising the side panel design once we have finalized dimensions and results for the cameras for the UND payload, finishing the mission timeline for the UND payload, as well as acquiring the UND payload. We would also like to compete for the NASA CSLI, which is the NASA CubeSat Launch Initiative, which is for our previous mission, the Softronics mission, that is due in November. So we are also working on that. For next semester, we are planning to work on complete hardware integration of the satellite, as well as complete and pass in-house long-duration environmental testing, as well as run a full lifetime software test on the satellite. Any questions?